Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I will be going over how to find the pH of a polyprotic acid solution. So I'm going to go over two problems. It's going to be basically the same as before, where we're going to just look at the first proton and then see what the equilibrium concentrations are after that first proton. The reason we can do that is because if you look at the Ka values of the first and second proton, the first proton has a much larger Ka value than the second proton here. So you can see here it's 8.0 times 10 to the negative 5 for the first one, and it's 1.6 times 10 to the negative 12 for the second one. And so that indicates that the amount of H plus that's given off by the second proton is negligible compared to that of the first, so we can ignore it. So we'll just do our normal ice table. So the initial concentration of the species that we're interested in for the ascorbic acid is 0.100. Water we're going to ignore because liquids and solids don't change during the reaction. Their concentrations don't change. And so that means we are going to have 0 or approximately 0 here. Or we'll have 0 here, and we're going to have approximately 0 amount of H3O minus to begin with. So there's our initial conditions, and now we know that the reaction is going to go towards this way to create product. So that means we're going to lose some of our ascorbic, so in terms of minus X, and we're going to gain an X amount of the monoprotic acid, or the conjugate base. And then you're going to gain some of the HCO plus, the hydronium ion. And then you add these together to get your equilibrium expression. So we're going to have 0.100 minus X, and then this will be plus X again, and this will be plus X again. And then now you can put this together for the Ka1 expression. So Ka1 is equal to 8.0 times 10 to the negative 5, which is going to be equal to, and then it's the concentrations of these two over the concentration of the acid. So concentration of HC6, H6O6 minus times H3O plus concentration over the concentration of the acid, H2C6, H6O6. Both of these are X, so this is going to be equal to, so 8.0 times 10 to the negative 5 is going to be equal to X squared over, and then this is the expression, this expression right here, 0.100 minus X. And so we can do the X is too small approximation. The reason for that is because if you look at the original concentration compared to the Ka value, it's much different, vastly different. So it's a good indication that you can do that. We'll have to double check that later. So I get rid of the X there, so it's X squared over 0.100. So I multiply both sides by 0.100, and then I square root both sides to get rid of the X squared. And if I do that, I get X is equal to 2.8 times 10 to the negative 3. So this becomes 2.8 times 10 to the negative 3. And now I should double check this to make sure. So I'm going to do the 5% rule. I take the 2.8 times 10 to the negative 3, divide it by the original concentration of the acid, 0.100, multiply that by 100, and I'll get the percent dissociation, or ionization, I should say, and that comes out to 2.8%. So 2.8%, that's less than 5%, so that means that this is a valid assumption. So the X is too small is a valid assumption. So I need to find the pH. So what I found here is X. X is the amount of hydronium ion. So now all I need to do is take this X value here, take the negative log of it, and I'll get the pH. And when I do that, I get a pH of 2.55. So that means that gives me a pH equal to 2.55. Let me write that better. So 2.55 is the pH. Notice that I have two sig figs here. When you take the log of a number, your answer should have this same number of decimal places as the number of sig figs here. So I have two sig figs here, so I should have two decimal places, 2.55. So that's the answer to this question. Okay, now what about this problem right here? Same thing, we're going to do the same thing. Notice the Ka values. Ka is 4.3 times 10 to the negative 7. Ka2, the second proton, is 5.6 times 10 to the negative 11. They're closer, but still it's quite different, so that this Ka value is very small. So that means that the second proton, is not really going to contribute very much to the overall concentration of H3O+. So you can ignore it. So we're going to look at the first proton coming up, and we'll do our ice table with that. And we'll use our ice table to figure out how much H3O+ is formed from the first proton. And so we take our initial concentration, 0.050. That's what we started with. The amount of H3O+ is negligible at this point, so we'll say 0. We have 0 amount of that. And so we're going to lose an X amount of this reactant. We're going to gain an X amount of H3O+, and we're going to gain an X amount of HCO3 minus. Okay, so then we just add these together. So 0.050 minus X, and again this is plus X plus X. And so now we can do our expression of the Ka value. So again, Ka1 is going to be equal to, where's our Ka1? 4.3. So 4.3 times 10 to the negative 7. And that is going to be equal to the concentration of these two over the concentration of this one. So if we write this down here, this will be 4.3 times 10 to the negative 7 is equal to the concentration of H3O+ times the concentration of HCO3 minus all over. Alright, sorry about that, my computer died. So where was I? I had 4.3 times 10 to the negative 7 is equal to the H3O plus hydronium plus ion concentration multiplied by the HCO3 minus concentration divided by H2CO3 concentration. And then all I'm going to do is substitute the X values for my equilibrium concentrations. So these are X times X is X squared. And then this gets put here, so it's 0.050 minus X And so we'll do the x is too small approximation, and we'll test that to see if it's valid later. Now all I need to do is multiply 0.050 by both sides. So I'm going to multiply it here and here, and then square root the answer. And then when I do that, I get x is equal to, and so the answer is 1.466 times 10 to the negative 1.466 times 10 to the negative 4. And paying attention to sig figs, we have 2 sig figs here, so we should only have 2 sig figs here. And then, since the contribution of H plus concentration is negligible with respect to the second ionization of the hydrogen, the second hydrogen, we can ignore that. But let's double check this. So what I need to do is take this value. We need to see if this is validated by the 5% rule. Take this, divide it by that, multiply by 100. And so if we do that, we'll divide this by 0.050, multiply by 100, and we get 0.29%. So again, it's less. It's less than the 5%, so it's valid. Okay. Okay, so this is validated. So now we have x is equal to this, and x is also our hydronium ion concentration. So all we need to do is take the negative log of this. So the negative log of 1.4 times 10 to the negative 4, or 466 times 10 to the negative 4. That will give us our pH. And we get 3.83. So the pH is equal to 3.83. And that's how you figure out the pH of a polyprotic acid. So I hope this was helpful. If you like this video, if you like my videos, then please like, share, subscribe, hit the notification bell, and put a comment in the comment section. Thank you for joining me, and I'll see you next time.